Okay, so this is Unit 2, the basics of differentiation. So in calculus, we are very often interested in not only a particular value, but how quickly that value is changing. We need to always keep in mind that the proper use of units is extremely important. So here are some pretty basic examples of calculating average rate of change. So if at 1 p.m. you were in Leesburg, Virginia, and at 3 p.m. on the same day you were in Washington, D.C., 40 miles away, what was your average speed? So we know that we went 40 miles in a total amount of time is 2 hours. So our average speed was 20 miles per hour. If the number of bacteria in a culture over time is described as B of T is 2 to the T, where T is given in hours, what is the average rate of average increase in bacteria per hour between T equals 2 hours and T equals 5 hours? So we know that we're going to find B of 5 minus B of 2 over the time change, which is 5 over 2. So B to the 5th is B of 5 is 2 to the 5th minus 2 squared over 3, which gives me 32 minus 4 over 3, or 28 over 3 bacteria per hour. So what we have essentially done is we find that the average rate of change is essentially the slope formula, f of b minus f of a over b minus a. Or if you remember from Algebra 1, y2 minus y1 over x2 minus x1, well, we wrote that as the change in y over the change in x, delta y over delta x. So in the diagram at the right, the dotted line shows a secant line. The slope of this line is the average rate of change from the point 1 to 4. So the average rate of change is going to be, we want f of 4 minus f of 1 over 4 minus 1, which gives me 5 minus 2 over 3, so our slope is 1. Now, suppose we wanted to discuss how quickly the value of the graph was changing in the instant that x is equal to 1. We can improve our calculation by selecting progressively smaller intervals. Eventually, the interval becomes so small that we call this value the instantaneous rate of change, which is the slope of the tangent line. And in this case, it is the negatively sloped line in the diagram. Based on the diagram, we can see that our slope is approximately, so instantaneous rate of change is approximately -2, which is very different than we found for our average rate of change. So how can we determine the quantity if it's not provided? And if we allow h to get smaller and smaller, as shown in this diagram here, we can approximate this rate of change. So what we want is to evaluate a limit. We want the limit as h approaches 0. This is f of x plus h. This point is f of x. So we want to find the change in the y, f of x plus h minus f of x all over h. This calculates the instantaneous rate of change, and this is also going to be called the limit definition of the derivative. So a derivative, usually described as, and we're going to write this as f prime of x, is the function that allows for the calculation of the instantaneous rate of change, or the slope of the tangent line, at a particular value. So we can write this as f prime of x, dy dx, y prime, or d dx of x. So we're looking for f prime of x if f of x is equal to x squared plus 1. So we know that f prime of x is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. So that's the limit as h approaches 0 x plus h quantity squared plus 1 minus x squared all over h. So the limit as h approaches 0, this expands to x squared plus 2xh plus h squared plus 1 minus x squared, and I forgot to put the plus 1 up here, plus 1. And let's throw that in some parentheses. All over h. So then we have the limit as h approaches 0. We have the x squareds cancel out, the 1's cancel, and we have 2xh plus h squared over h. Then the limit again as h approaches 0. This becomes 2x plus h, which equals to 2x. So now we want to go ahead and calculate f prime of negative 2, which we see is negative 4. F prime of 0 is 0, and f prime of 1 is 2. Now, what this means graphically is that the slope of the tangent line at x equals negative 2 is negative 4. The slope of the tangent line at x equals 0 is 0. And the slope of the tangent line at 1 is 2. So let's go ahead and do another example. And I'm just going to set up example 2 and example 3, and I'd like you to go ahead and continue through. So we know that I'm going to write this as dy dx is equal to the limit as h approaches 0. And I always go ahead and write the equation first so that I don't lose track of it. So limit as h approaches 0, we have the square root of x plus h minus the square root of x all over h. So I'm going to let you continue that one from here. You should recognize it as one where you need to multiply it by the conjugate. For example 3, we want to differentiate, so we want f prime of x. Again, our limit as h approaches 0, f of x plus h minus f of x all over h. It's the limit as h approaches 0. This is 1 over x plus h minus 1 over x all over h. And this becomes a complex fraction that you need to simplify. So then we want to find, and you should get for this one, and I'm going to go ahead and solve that out, but I do want you to keep going. This should be negative 1 over x squared. And since we want to go ahead and find the equation of the tangent line, so we know that f prime of 2 is going to be negative 1/4. We need f of 2, which will be 1/2. So our equation of our tangent line is going to be y minus 1/2 is equal to negative 1/4 x minus 2. Now, I'm going to set up example 4 for both equations, and I want you to carry them through and then see if you can figure out why the two derivatives are. All right, so with this, we have that f prime of x is the limit as h approaches 0, f of x plus h minus f of x all over h. So for the first equation, we have f of x is 2x squared minus 3x plus 1. So we have the limit as h approaches 0, 2 times x plus h quantity squared minus 3 times x plus h plus 1 minus 2x squared minus 3x plus 1 all over h. And then the second equation is f of x is 2x squared minus 3x plus 4. So we have the limit as h goes to 0 of 2x plus h quantity squared minus 3x plus h plus 4 minus 2x squared minus 3x plus 4 all over h. So go ahead and finish those two derivatives, and then your question in the video will be to explain why these two derivatives are the same. Okay, so it's important to note that a function must not only be continuous, remember that three-part definition, in order to have a derivative value, but that the function must also not have a sharp point there either. The curve must be smooth in order to have a derivative value. So this is because of the derivative being defined as a limit. So therefore, differentiability at a point implies continuity, but not necessarily the other way around. So 4 different ways that a function could fail to be differentiable. If the x value is not in the domain of the function, vertical asymptote. The function is not continuous at that x value. There's a jump or a hole. There's a sharp point at that x value, the vertex of the absolute value graph, for example. Or there is a vertical tangent line at that x value. So for which values, looking at example 5, for which values of x does the function shown at right have no derivative value? So I can see that at x equals -1, there will be no derivative because it's a sharp point. And at x equals +1, there's a discontinuity. So x equals -1 is a sharp point, and x equals +1 is a discontinuity. Okay, so looking at this graph, we can see that we have positive derivative values where our slope is positive. So that looks like between -1 and 0, and then again from 1 to infinity. I can see that it looks like my slope has a negative value from -infinity to -1 and 0 to 1. And lastly, I can see that my slope appears to be 0 when x equals to 0. So a good way to think about the differentiable functions is that they are locally linear. That is, and as we saw in your Desmos activity, a function that is differentiable at a point closely resembles its own tangent line at that point. If we were to only look at a very small portion of any differentiable function, that portion would become extremely straight. So we can use this relationship to approximate values of functions by using the tangent line ahead. So given that the tangent to f of x, so let's write f of x is equal to x squared minus 3, at the point 2, 1 gives us the tangent line of 4x minus 7. So if we approximate the value of the function f of 2.05 using the tangent line, we can say that y is equal to 4 times 2.05 minus 7, which gives us that y value is going to be 1.2. Now, would like you to evaluate f of 2.05 using f of x in a calculator, and then note the similarity in the answers.